See, in hydrocarbons, first part is about alkanes. Got it? What all things we need to understand is that C1 to C4 are generally gases, C5 to C17 carbons, whether they are in a branched form or not, they usually exist in liquid. C18 and above will be usually solid, waxy solids. Generally, melting point and boiling point and any other physical characteristic mainly depends on molar mass. If that is increasing, boiling point usually increases because the van der Waals forces of attraction would be more for a bigger size molecules. So therefore, N-pentane will be greater than isopentane than neopentane. Melting point is the only exception which you will find where even and odd would have more even and odd. We need to check out based on symmetry. Okay, so you can say based on symmetry, based on symmetry, even carbon chains usually have more melting point compared to odd. But that is again restricted only after carbon 6 onwards. But again, it will keep varying a lot. How much you need to remember is this much. Pentane towards propane, how does it vary? So pentane, then butane, ethane, methane, and propane. Okay. Next, heat of combustion. Heat of combustion mainly depends on number of carbons. Okay, how many number of carbons we have. So you can see C5, C6, C5, C4, C3. This is how the heat of combustion would be. Okay, more the number of carbons, more is the heat of combustion. If isomeric alkanes are concerned, then suppose if you have C5 with a straight chain, branch chain, and further branches, more the branching, less will be the heat of combustion. Okay. Next, if you notice the chemical properties of alkanes, first and most important property is about the radical mechanism. First is free radical mechanism. Heat or light is needed to make this reaction. Mainly, you can see methane when you react with chlorine is one of the examples where heat or light is used to create alkyl halides. Every time there is an free radical mechanism, first step is called initiation, where you prepare a radical. So Cl2, on heating, it will be slightly endothermic to break the bond here. And then second step is about propagating that radical into further radicals. So you can see Cl dot converting into CH3 dot. That is called further propagation. Okay. Next you can see CH3 dot plus Cl giving CH3Cl plus Cl dot, which means this CH3 dot will further react with Cl2, create one more radical Cl dot. And that Cl dot will again react with CH4, create one more radical. So this is how the propagation keeps on happening. Usually the hydrogen radical is extremely unstable, so the possibility that H dot will be formed is very rare. And then CH3 dot reacting with Cl2 finally will give you CH3Cl. Okay, so this is how the radical, would keep on forming more and more propagation will take place. Any radicals that are present, may it be like Cl dot or CH3 dot, they can terminate as well after a while when most of the reaction is done and some few radicals, traces of radicals are present, they can terminate to give a very small composition of these products. Now, usually these two propagating steps are the most lowest steps. That is CH4 plus X dot giving CH3 dot plus HX, while CH3 dot plus X2 giving CH3X. Now, usually if you notice the case for fluorine, the first step is also highly exothermic, the second step is also highly exothermic. That is the reason why it will make highly explosive reaction. So much so that the carbon-carbon bonds will also break in that. Okay. Therefore, halogenation, fluorination on radical alkanes would be highly explosive reaction. While if you do chlorine, the first step is endothermic, but the second step is sufficiently exothermic. Makes it explosive but not very strong. So that means you can control this reaction, but it is highly reactive as well. But if you notice the case of bromine, the first step is slow because it is endothermic. Second step is slightly better, but overall reaction is still exothermic, which makes it the reaction could happen but the energy release here will be very less. So which makes it very choosy and selective. While in case of iodine, the first step is highly endothermic. Even though the second step is exothermic, overall makes it highly endothermic reaction, which makes the reaction to go more in the backward direction. Got it? So overall reactivity, if you notice, fluorine is greater than chlorine, bromine, and iodine. Okay, because of this explosion. Now you might wonder, sir, why we are relating delta H, for spontaneity of the reaction. Usually we should see delta G, right? Delta G is Gibbs free energy. Now notice this one. Suppose if we have delta H and delta G, right? So then what do we need to check here? Check once here. Suppose if you notice these two reactions, what will be the delta S of the reaction here? If you notice properly, there are two reactants and two products, which means hardly there will be any entropy change of the reaction. So I'll write it as delta S entropy change of the reaction is zero. And delta H of the reaction, imagine it is endothermic, then this is less than zero. And what will be delta G? Delta G will be equal to delta H of the reaction minus T delta S of the reaction, correct? So you can clearly see that this factor is ignorant now because it is almost zero. So delta G mainly depends upon which factor? Delta H only. So if delta H is more negative, that makes delta G also to become more negative, and that's how it becomes more spontaneous. So if delta G of the reaction is negative, it implies delta G of the reaction will also become negative and reaction is more spontaneous. It's more spontaneous. Okay. So that's how you can see that reactivity of this F2, Cl2, Br2 and I2 varies. Next, in case of I2, one thing we learned that CH4 plus I2 is giving CH3I plus HI. Delta H overall is positive, but which means the reaction would be lying mostly on the backward direction here. Which means if by chance, imagine if I take this HI and oxidize it to make it I2, then using Lee-Shadler's principle, we can say if the reactant concentration is increased and the product concentration is decreased, the reaction can always drive in the forward direction. And that's what we are trying to do. So this HI is being oxidized by mild oxidizing agent that like dilute HNO3 or HiO3 or HGO. HiO3, how the reaction works, you see this one. HiO3 will react with Hi, will convert into H2O plus I2. That's how the oxidation could happen. And this is one way of increasing the quantity of Hi and making it more radical based mechanism. Okay. Now, experimentally, what has been observed, if I take propane, react with fluorine, I was able to get 80% of fluorine on a 1 degree position and only 20% on the 2 degree position. While with chlorine, this was around 60 to 40. But when it comes to bromine, it was extremely more on the radical, which is at more substituted place, that is 2 degree place. Which means if you compare the stability of radicals, we know that 3 degrees greater than 2 degree greater than 1 degree and methyl radical. That means if I compare the radical stability, since 3 degrees more stable, bromine is driving more towards this part. Okay, so from here I can make one important conclusion that chlorine is more reactive and less selective and less selective, while bromine is more selective and less reactive. Reactivity is very slow, but whatever the product form is a highly selective product. Okay. Using this experimentally, what has been observed that if there is a chance of going on 1 degree position, 2 degree and 3 degree position, these were the rates of chlorine and bromine found. So 1 is to 3.8 is to 5, while for bromine it is 1 is to 82 is to 1600. That shows that 3 degree position has extremely high rate compared to 2 degree and 1 degree. Okay. This was the rate of substitution of halogens. Now, as an example, I have written it here. You can see what is the percentage of product of chlorination and bromination. So if you notice this 3 degree position here, and this is 1 degree position here, chances are you can get 1 degree and 3 degree as the products. And contribution wise, if you notice, there are and three hydrogens. So 9 cross 1 by 9 cross 1 plus 1 into 5. The rate of going at 3 degrees 5 into 100. That makes it 64% and the other one is 36%. And the same thing if you check out for bromine, the 1 degree is hardly 0.5%, 99.5% is only 3 degrees. Okay. Next thing is, if you notice the stereochemistry of this radical substitution, bromine could be going at this primary position or secondary position for N-butane. And you know that this is going to be major product. But at the major product, it is also gaining a chirality. It is also gaining a chirality, which means at this position, when a radical is present, a radical carbon will be sp2 hybridized. And Br dot, which is coming with a single electron, it could come and make a bond from the top of this or from the bottom of this orbital. So the chances are it can go for 50% from the top and 50% from the bottom. Therefore, we will end up getting 50% of, dextro form, if this is dextro form, right? And 50% of that levo form, correct? Or if it is single chiral center, you should always speak with absolute configuration. If based on absolute configuration, one is plus R, the other one, I mean, if it is R, the other one has to be S config. Okay. So this ability to get 50% dextro and 50% levo is called racemization. So the possibility is we will get a racemized product in case of radical substitution. Okay. Now check this out. How many substitution products, including stereo, are possible for monochlorination? If I do monochlorination on this one, where all we can write, check pH here. I can write one chlorine here, and I can write one chlorine here, and I can write one chlorine here, and I can write one chlorine here. See, usually it should happen even on the phenylic case, but that will be usually given in the exam. Okay, that exclude phenylic substitution. Phenylic substitution. So if I exclude that phenylic substitution, now you would notice that there is a chiral center here. There are two chiral centers here. There is one chiral center here, and there is one more chiral center here. Therefore, I would get two products here. I would get four products here. I would get two products here, and I would get two products here. Correct? So total, I will get for 8 plus 2, 10. So 10 stereo isomers I will get. Give it up. So I hope this first part is clear. See, see this percentage of chlorination and bromination in this case. First, first let me write the question here. Suppose I have this compound. For this, I am doing chlorination. Just now, we have learned how to identify the isomers. Let me put that in perspective here. So I can get one chlorine here. I can get one chlorine here. I would get one chlorine here, correct? And lastly, I would get one chlorine here at the terminal position. Now, percentage wise, if you notice, there are 1 degree carbons, 2 degree hydrogens, 3 degree hydrogens. 1 degree, I have 9 of them of two kind. 9 of two kind. Why? Because putting chlorine here and here is same. But putting chlorine here is different because you will get two different types of products. So this is categorized into again two 6 and 3 type. 2 degree kind there is only one, and that too two of hydrogens. 3 degree I have one. Okay. The contributing factor for 1 degree is always 1. For 2 degree is 3.8, and for 3 degree it is 5. This is the rate ratio with which the chlorine will attack. Now, if I need to calculate the percentage of this product A, B, and C, A, B, and C. So I'm trying to figure out how much is the percentage of A now. So percentage of A will be equal to chances of coming chlorine here is 6 times into 1 divided by 9 times into 1 plus 3.8 times into 2 plus 1 into 5 into 100. And this is about percentage of A. Percentage of B will be equal to, right? I have one time here. So therefore, one time of 5 divided by 9 times of 1 plus 3.8 into 2 plus 5. And lastly, percentage of C, if you notice, it is 2 times of 3.8 divided by 9 into 100 here. 9 plus 3.8 into 2 plus 5 into 100. And lastly here, percentage of D. Percentage of D, if you notice, that is equal to again 3 times of 1 by 9 plus 3.8 times of 2 plus 5 into 100. So now if you compare the percentages, just check out the numerator value. Numerator value here is 6, 5. This is approximately 7.5 here, and here it is 3. Okay. So percentage composition wise, if you compare out of all of this, then you can notice that C is greater than A, is greater than B, is greater than D. Okay. This is the percentage composition of chlorination. Okay, beta? The second reaction of alkanes is about aromatization. That is how to convert this into an aromatic compound. If we have N-hexane, react that with Cr2O3 and Al2O3 at around 100 degrees and 10 to 20 atm pressure, then you should be able to convert that into this form. Acha, are these the only reagents? No. You can take V2O5, we can take MO2O3 here, and we can individually take Cr2O3. We can take Fe2O3 mixture, Fe2O3 and Cr2O3 mixture. Any of these type of a mixture with this strong heating at around 773 kelvins, if you use it, then they all will convert into benzene forms. If it is N-hexane, I will get toluene as a major product. If it is N-octane, I would be able to get xylenes, which is at orthoxylene, metaxylene, and paraxylene, while we can also have ethyl benzene. These are the products you can have. Clear? So this type of form of reactions is called aromatization. Now, aromatization can also occur, right? Let me put that here. Alternative aromatization. Alternative aromatization. That is, in case if you have an cyclohexane or cyclohexane or isolated diene, or you can have conjugated diene. Any of these form, if you react them with sulfur and heat, or selenium and heat, or polonium and heat, or platinum and heat, or palladium and heat. If you see any of these, they all will do the same thing again. All of them will do only one reaction here, beta. They'll all convert these compounds into benzene form. This is also a part of aromatization. Got it? This is another alternative aromatization form. Next, pyrolysis. Pyrolysis is a reaction where we are trying to break the molecule into smaller pieces. Got it? If you react this with, at around 1000 degrees for methane, it can convert into a black color carbon, that is powdered carbon or a coke, and H2 gas can be released. But if you are heating ethane at around 500 degrees, you can get ethene and H2. If it is propane, it will give you bond broken products also. That is propene, ethene, and methane along with H2. Okay. This way, pyrolysis reaction can be carried out. You will usually get a smaller alkenes and methane and the respective alkenes of the given molecule. Okay. Next one is about isomerization reaction. Next one is about isomerization reaction. Yeah. Now, when it comes to isomerization here, okay, one second. I'll take you through the mechanism also in this case. Okay. See, in case of isomerization, basically here we are trying to use a small bit of alkene for making this reaction to happen. We always take some small amount of alkene to make this reaction to happen. See how? Basically, if this compound has to convert into this compound here, so which is an isomer form of this N-butane. So we will take a small amount of alkene here, and then we will try to react that with anhydrous. This has to be anhydrous. It should not be as aqueous at all. Okay. So we'll take an anhydrous form of it, and then we'll make a carbocation form here. Okay. So we make this carbocation form, but this alkene which is taken is in a very small composition. Got it? It will be in a very, very small composition. Okay. Right. Next, once we get this, if you notice here, we will try to see how to generate a more stable carbocation in this case. How to generate a more stable carbocation. So on this alkane form here, imagine in the presence of AlCl3, you can think this way, beta. AlCl3 plus HCl is basically helping to convert into AlCl4 minus, and that's how it is releasing H plus. And that H plus we are using for a preparation of small amount of this alkene. Got it? And then when you take this alkene here in the presence of alkane, given alkane here, what would happen here is this will release out H minus. It will release out H minus and try to convert into carbocation, and that's how convert into this alkane form here. And that's how convert into this alkane form. And this movement of hydride is usually happening at a higher temperature. So that's why high temperature is expected in this case. Got it? High temperature is expected in this case. Now, once you get this carbocation form here, what you would notice is that this methyl group will try to shift here, but for that a pressure is required. On shifting this methyl group here, correct, you will be able to generate this positive charge here. And from this alkane, the H minus which you took, right? So here, imagine like this, same H minus will come here and combine back to convert this into an isomerized product. And here you would have this as carbocation once again. Sorry, not from here, from here. This hydride will attack here. Get a carbocation once again. And this carbocation form, Cl minus from AlCl3 will take away this H plus to remove out that alkene. So have you noticed that you took an alkene and that alkene has come out. But what it internally did, it it formed a carbocation and initiated a carbocation formation on the main alkane, and that alkane underwent rearrangement and taking out this H plus. And this usually happens at a high pressure, and that's how you'll get an alkane form here. Got it? So this is a typical mechanism which is observed. This hydrate shift is not, this methyl shift is not that easy to occur. So this reaction is very slow, and this is the rate determining step, RDS in this case. Okay. This step is called the isomerization step. Okay. So I hope this part is clear. Check. Next one is about oxidation reactions. If I take methane, react that with O2. Okay, if you react this with O2, then I would see that in the presence of red hot copper tube or red hot iron tube with high pressure and high temperature, usually this temperature, if it is only copper taken, is around 523 and 100 atm. Such high pressure, then you will be able to convert into methanol and H2O. Okay. If it was for molybdenum, if it is for molybdenum, then temperature is around 230 and 100 atm, and it will convert into formaldehyde and H2. For this, there are no mechanisms, beta. These are industrial reactions. We have to directly remember it. In case if it is manganese acetate at high pressure, if it is be taken, it will convert into a formic acid and H2O. Right? And lastly, if it was for KMNO4, KMNO4 only reacts with a 3-degree alkane, which must have a 3-degree hydrogen to remove and make a stable radical here. So that stable radical will take the nascent oxygen from KMNO4 and on heating, this is on heating, and convert that into 3-degree alcohol. And this is only way where we will see alkanes reacting with KMNO4. Otherwise, alkanes have no reaction with KMNO4 in general. Correct? So this is what we expect the reactions to take place. Okay. Next, nitration. If you compare the nitration part here, in case of nitration, you would see any alkene when you treat with concentrated HNO3, okay, at around 450 degrees centigrade, that will convert into nitro products here. That will convert into nitro products. You always think this way. In nitric acid on heating, the bond breakage is like HO dot and NO2 dot. HO dot and NO2 dot. Okay. So NO2 dot is a radical which will initiate this reaction, and it is always a vapor phase reaction. That means these reactions cannot be in liquid state. So in a vapor state reaction, you will see CH3, right, will give this product, as well as it will break between carbon and carbon, and those radicals will terminate to give CH3 NO2 product as well. Rest will be H2O because that hydrogen has gone. So that will convert into an H2O form. Same way, if you have propane, you will be able to get at 1 degree, 2 degree position, as well as bond broken nitro with methyl nitro also. So all these nitro forms are possible here. Got it? So I guess this reaction is clear. Okay.
Yes, sir.
Usually this is more feasible for higher alkanes. Okay. Higher alkanes. Carbon-carbon bond usually breaks homolytically, and lower substituted alkanes are, more easily formed in this case. Got it? Next. Check out sulfonation. Sulfonation is about H2SO4 on heating giving HO dot and SO3H dot. Same way, just like this case, propane, if you react with this one, now these radicals does not release the amount of energy to break carbon-carbon bonds. So carbon-carbon bond breakage is not observed in this case. So sulfonation usually will be more observed in 3-degree position because it is a slow step, and it reaction is happening more selective way, just like bromine. Here, 3-degree would have more reactivity than 2-degree, 1-degree, and methyl. Okay. So this is how the sulfonation would work in this case. Clear?
Yes, sir.
Right. So this is the sulfonation cases, beta. Any form of sulfur is given. Acha, in sulfonation also, one thing you need to understand, it cannot happen just with methane and all. Usually it needs to have propane and above. Okay. So reactivity, reactivity observed for carbon 3 chains and above. Chains and above. Right? So this would be for preparation of alkanes. Next. If you compare the, those were the properties of alkanes. Now, if you compare the preparation of alkanes, what all reactions we can use here? The first reaction being catalytic hydrogenation of alkenes and alkynes. See, this is an alkene. When you react with any reagents, it could possibly get an alkane form like this. Same way, an alkyne can also react with some reagents to get an alkane form like this. What are the typical catalysts that can be used? See, H2 by nickel at around 200 to 300 degrees centigrade. Anytime we use the palladium, platinum, all of this, right? I could also use, or I'll write down this H2 by palladium also, or H2 by platinum also. If I'm using these reagents, if I use any of these three reagents, these are called Sabatier-Sanderen's process. Nickel alloy, nickel, when you take an aluminum alloy and react that with NaOH. See, typically how the reaction works is nickel plus aluminum plus NaOH. What happens is aluminum dissolves in the presence of NaOH. So that makes this as Ni and aluminum's alloy, right? In which you have some, Na nickel plus NaAlO2 and release of nascent hydrogens. So it is a source for nascent hydrogens, and these nascent hydrogens will get accumulated on the surface of nickel. And that type of highly reactive nickel is called Raney nickel. This is called Raney nickel. If I take carbon, coke, and add it onto the platinum surface, it only increases the activity of palladium, and carbonated palladate will also be a much better source for catalytic hydrogenation. PtO2, another way of increasing the activity is platinum to get in an oxide form, and then H2 gas will get absorbed more easily. Okay. Another catalyst is nickel boron and hydrogen catalyst, which is also called as P2 catalyst. But the problem with the P2 catalyst is from alkynes it can reach to alkenes, but further to alkanes it cannot go. So major product will be only about alkenes, not an alkane here. Okay. See, how does the mechanism typically work here? This is a metal surface. On the metal surface, hydrogen first get adsorbed in the grooves, and then alkene or an alkyne will come close to the vicinity of these hydrogens, and that's where the bond cleavage can take place. It can convert into radicals. So you will have two dots here that will interact with the hydrogen dot. This will also convert into radicals. So the dot and dot interaction here, and bond breaking here, and dot interaction here, and a bond breaking here. Here I forgot to make this one. So this is a transition state. This one is a transition state. In the transition state, you will notice that you are getting a four-membered cyclic transition state. MCTS, remember that word MCTS. MCTS means membered cyclic transition state. So this type of addition, if at all it is happening from the same side, is always called as syn addition. So you notice that there is a syn addition undergoing here. So H2 is added from the same side. That's why it is called syn addition. So suppose if we have a cyclohexene and deuterium has been added in the presence of nickel, both deuterium should be on the same side. Well, in this case, because it is a meso form, these two molecules are same. These two molecules are same, but it is not necessary always they have to be same. For example, if you notice this A and B product here, suppose there is an alkyne here. H2 is been added for the first case, which is a syn addition. Syn addition will give you cis product here. So which means double bond here, hydrogen here, and hydrogen here. This is the first product form. And this is a cis molecule. And on a cis molecule, if you add a deuterium here, correct, it will give us this product. That is deuteriums on the same side, hydrogens on the same side, methyl on this, up and down. This is a Fischer representation. Fischer representation. The Fischer representation. Clear? Now let us do some questions related to this Fischer representation. See, what I'm trying to
Sir,
say,
can I wish the
one
washroom and come
second,
back?
one second. Now notice this. Let us generally understand stereochemistry of alkenes. Check. In generally, if you have a three-dimensional structure, I can write it in two-dimensional structure in this form. Hydrogen, 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 hydrogen. This is called the sawhorse projection. Sawhorse projection of ethane. The Sawhorse projection of ethane. Okay. And in this projection, if you notice, this hydrogen and hydrogen are exactly on the same lines. These two are on the same lines. These two are on the same lines. Such type of a projection is called as the eclipsed projection. And the type of conformation is called eclipsed conformer. So this is an eclipsed conformer. The same sawhorse projection I can write down this time, but slightly in a different idea here, where the hydrogen's position is changing like this. Got it? So if I put it this way, now it is like we have anti-parallel hydrogens. These two are anti-parallel. These two are anti-parallel. These two are anti-parallel. And there is a center of symmetry in between them. So such type of conformations are called as staggered conformations. Staggered conformations. Okay. Now you could make this projection into a top view of it. So these are this kind of view when you are writing it on paper, these are called a side view. So it is like I have a molecule in front of me and watching from the side, and then they're taking a picture of it. So I would be able to appear either I'll be able to see the molecule in this form or this form. But if I want to make it as a top view, then I can only make a top view when I have an eclipsed position. I cannot make a top view when it is in a staggered position. So that is one thing we need to understand. So this is an eclipsed position, correct? And if I want to make a top view, another important thing is I need to represent the same molecule in a way that it is having the single line here and the other two lines pointing upwards like this. This is the way I need to keep it now. Okay. So you can imagine as if I'm tilting the entire molecule upside down. So then I have these two hydrogens here. And then I need to watch it from the top. I have to watch the molecule from the top here like this. So if I watch it from the top here, then it appears that one of this hydrogen could be, like pointing towards my face, and one could be pointing towards my foot. So if this could be the upwards, this could be the bottom hydrogen. So in that case, how do we need to view it here is that you make a big line here with one hydrogen up and one hydrogen down. And then you make two more horizontal lines here, correct? In which this group, any of these two groups, correct? Any of these two groups here on the left and these two groups on the right. So these groups are on the left and these groups are on the right. This kind of a projection of a top view where three-dimensionally, if at all I write it, it is like this. There should be a carbon line on the same plane. Then there is a hydrogen going in and another hydrogen going inside And then there are two hydrogens here coming outward like this. And again, I have two hydrogens coming outward in the next carbon here. This is the three-dimensional representation. So for this three-dimensional view on a two-dimension looks this way. And this is called the Fisher projection. This is called Fisher projection. Now, if I take this three-dimensional structure, imagine I take this three-dimensional structure and make this methyl hydrogens as methyl. Make these hydrogens as methyl. Okay. And this horizontal hydrogens as, let's say, some OH group here, like this. OH group here. Correct? Then this is called the spine. This is called the spine. Correct? Spine of the structure. And these are the wings or hands. You can see these are the hands. And this is the spine. The vertical line is the spine. Got it? So in a Fisher projection, I would be able to represent that as CH3 here, CH3 here, then OH, OH, H and H. In case if two similar groups are on the same side, if two similar groups are on the same side, then you call this as erythrokind. This is called erythrokind. Okay. Similarly, if I take a Fisher projection here and keep this OH on the left hand side here, one OH on the left hand side here. So now this H is here and this OH is on the left. Then this is called threokind. This is called threokind. This is called threokind. I hope the basic idea is clear. When do you see it is erythro and when do you see it as threo? Okay. Now notice this case, beta. Suppose I have a double bond group here. Okay. So I'll put the double bond like this. This is double bond. And I have a methyl here and a hydrogen here. Methyl here and a hydrogen here. Okay. This hydrogen is going inside. So this is methyl here, methyl here. One hydrogen is here, one hydrogen is here. And then there is a metal surface here. This is a metal surface which has deuterium on top here like this. And it is getting attracted from these two positions to make a bond. Correct? So if this is the bond, how does it look like after getting added? After getting added, now I can say that two methyls will be on top here this way, correct? And these hydrogens will be on the left here, and this deuterium would be here, correct? This is the way it will get added, okay? Because you can see both the deuteriums are making a new bond, but on the same side. So these two are on the same side, correct? Now, if I put this molecule into a Fisher projection, okay, in the Fisher projection, I have to always watch it from this way so that I can have a top view. This way I have to watch. So I will have this as the methyl group, two methyl groups here, and hydrogens could be on the left and deuterium could be on the right here. This is the kind of product you will get, correct? And what are we getting here? Erythrokind, which means if we analyze the stereochemistry, what I did here, I took a cis molecule, made a syn addition to generate erythro. Correct? This is what we did. So cis plus syn will always give you erythrokind. This is what we learned. Cis plus syn will give you erythrokind. Clear? Now, suppose if it is a trans molecule. So imagine this way. Again, I have carbon, double bond C here, and then I have methyl M and H here, and methyl and H here. Then there is a metal surface here on which I have a deuterium and deuterium here. which is getting added onto this one. As you see, the addition which will happen here, correct? We'll have carbon and carbon bond here. After addition, I'm showing. After addition, we'll have carbon and carbon bond. And methyl would be here. Deuterium has made a bond here. And hydrogen will be on the back side. And here, deuterium has a bond. Deuterium has made a bond here. But methyl will be down here now. And hydrogen will be here. Isn't it? Because now it is a three-dimensional molecule. So this one and this one will be behind. This methyl will come down like this if it is getting added. Okay. Now for that, if at all I rotate it here, so imagine on this bond, I have rotating it by 180 degrees. So if I rotate it by 180 degrees, what do I get? Carbon, I will have methyl, hydrogen, and deuterium here bonded to carbon, which have, as you rotate it by 90 degrees, you will get this as deuterium and hydrogen here and methyl on the top, correct? This is what you will get. So now if at all I put this in Fisher projection, I will get this as methyl and methyl with, if hydrogen is here, hydrogen is on the opposite side. Deuterium and deuterium all on the opposite side. Or I could write this plus, the chances are I could have deuterium here and deuterium here, then hydrogen here and hydrogen. Okay. So the product, how does it look like? This is also a 3O product. This is also a 3O product. When a similar group, when a similar group of a kind are on the opposite side of the Fisher projection, then that is called 3O. So this is also 3O kind. Clear? Chances are this can be 50% found. This can also be 50% found. Okay. So if this overall molecule is showing dextro rotation, this will show levo rotation because they are mirror images of each other, which means the resultant will be racemic mixture. The resultant will be racemic mixture in this case. Got it? Now, what has happened? I took a trans molecule, made a syn addition by which I was able to get trio. I got trio here. So from here, we will make a very simple conclusion here. That is cis plus syn addition will give you erythro. Got it? Okay. While trans plus syn will give you trio. Similarly, cis plus anti should give you trio and trans plus anti should give you erythro. This is the way you need to remember. And it works the reverse way also. The reverse way means if I take erythro and make a syn elimination, then I will get cis. And if I make trans and I make a syn elimination, sorry, if I take trio and make a syn elimination, then I'll get trans. And if I make trio and make an anti-elimination, then I will make a cis as a major product. If I take erythro and take out an anti-elimination, I should be able to produce trans. Okay. So there are many ways to remember it. Okay. One way to remember is this, that I will do CSE, that is computer science engineering. Clear? I will complete computer science engineering test. I will finish the test, correct? And also write a CAT exam, right? To make sure I'll eat well. Okay, this way. So you can remember it this way as a loop. CSC, test, CAT exam, or eat. And it works either ways. Clear, beta? See. Suppose if I ask you a question like this, where I have compound given, where I have compound given this way. I have a fixed methyl position here with a double bond, and then D2 in the presence of nickel and heat is given. Obviously, I'll try to make it because this is a cis type of a molecule. This is a cis form of a molecule. Then what will I do? There is a methyl here. So I will make a deuterium addition like this. And this deuterium could be added from the top also. And this deuterium can be added from the bottom also, which means this way. Correct? But now if you notice, are these two mirror images beta? No. So what are these? Pair of diastereomers. Pair of diastereomers. Clear? So we cannot say exactly how much percentage, but we can say definitely this is a pair of diastereomers in general. Got it? Next. Another example, you see, imagine I already have a fixed configuration here like this with an ethyl group here, correct? And it is a trans molecule here. So this is a trans molecule. Then I have H2 by palladium and heat. So again, the logic is the same. I'll have ethyl this way, that is fixed. And now on H2, if you add here, as H2 is been, sorry, D2, not H2, D2. If D2 is been added here, correct? This I'll have hydrogen and deuterium. Here also I'll have hydrogen and deuterium. Clear? But if you represent the same thing in a Fisher projection, so what I could write? I will write three groups here like this from methyl to methyl, and there is one ethyl at the starting which has a fixed configuration. You can write it on the right or left depending upon its configuration, whether it is R and S. Then on a trans, when you add deuterium, it will always go with 3O kind. So this is one product I will get. And the other product is, without disturbing the configuration of that ethyl group here, you just need to do this hydrogen and deuterium shift here. So we can say that deuterium here, hydrogen here, and hydrogen here, and deuterium. Again, what are we getting? Pair of diastereomers. Alright. So this configuration is fixed, but the other two configuration is not fixed. So like that, you should be able to figure out what are the products given. Okay. So I think this point is clear. Ayush.
Yes, sir.
Now, suppose if I gave you different molecules here, and I want to figure out in which case the stability is more or less, and based on that, you need to figure out what is the reaction. See, for example, if I take a molecule this way, I have one double bond here, I have one double bond here, and I'm making this to add with nickel and H2, but this time I took only one equivalent. This time I took only one equivalent. Okay. If it is one equivalent, where should we add this? Got it? Right. So now if you notice that, you need to check out which one is more stable ring. Okay. So if you notice which one is more stable ring here, correct? See, suppose if you have to make an addition of H2 here, I have a cis kind also and a trans kind also. This side is trans kind. One note, important note, you should recall from isomerization is that in rings, in rings, carbon greater than 10 atoms, carbon greater than 10 atoms, stability, stability typically is trans more stable than cis. Trans is more stable than cis. Got it? Acha, if trans is more stable than cis, discuss how many number of carbons we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12, obviously it is more than, in that case, trans is generally more stable than cis. Okay. If trans is more stable than cis, then we do not react the trans part. Which one do we react? We react the cis part of it. So what should be the product here? In that case, this you will remove it out and make these two hydrogens to get added. That should be the product. Okay, this is another example. One more example, if you notice, suppose I have an 8-membered ring like this. I have a double bond here and a double bond here. Okay. Now you notice this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So if it is 10, definitely in this case, cis is more stable than trans. Cis is more stable than trans. So which means if I take nickel and H2 to add one equivalent only, then the product would be the one where whichever alkene is more reactive, that will react. So in that case, which means hydrogen and hydrogen will get added here. So this is major product. Got it? This is major product in this case. So you got to remember in which case what addition will take place. Okay. Next case, you notice that is about the rate of hydrogenation. Rate of hydrogenation. See, because hydrogenation happens mainly on alkenes and alkynes, you would see that more bulkier the alkenes and alkanes will become, less is the ability to come close to the metal surface. Because of steric repulsions, the pi bond is at a farther distance away from the metal surface. Therefore, if you notice, rate mainly depends upon inversely proportional to steric crowding or steric hindrance around C double bond C or C triple bond C. So this is the criteria on which you should look out for. Therefore, rate of hydrogenation, rate of hydrogenation will be most for triple bonded form with some group here, sorry, with some group here and CH3. Next is with two more groups here, CH3C triple bond C. So then comes double bond, CH2 double bond CH2, then CH3CH double bond CH2, then CH3CH double bond CH3, and then CH3 twice C double bond CH3, and lastly CH3 twice C double bond CH3 twice. So this is the rate of hydrogenation. So now, lot of questions are also framed on the basis of rate of hydrogenation. So where do we actually supposed to attack? Correct? Where do we supposed to attack? In that case, suppose I have double bond here like this and this way, and then I'm treating with D2 in the presence of nickel and heat, and only one equivalent was used. This is the example I'm giving. In that case, you will be adding on to the one which is less substituted. Because less substitution is the more important criteria. You will not see what is the stability of double bond and so. You will notice the stability of double bond only when the crowding is very, very similar. If the crowding is similar, then only we'll notice. Otherwise, the priority should be always given to crowding. Correct? Clear it up? Right. Next. A double bond here. double bond here, triple bond here, correct? So if I add deuterium here, D2, clear, of D2 and nickel here first, of only one equivalent, then obviously you will be, sorry, two equivalents. I'll have to make it this way. Yeah, like this. So if at all I take two equivalents here, two equivalents, so remove this double bonding. In that case, first addition will be about double bond here because deuterium and deuterium will come here first. And after that, this is for the first equivalent. First equivalent. When you add the second equivalent, now you know that this deuterium is more substituted. This double bond is more substituted. So where do we add the next deuterium? Deuterium will be added here. Okay, so this deuterium will stay with a double bond, but this will remain. So this is the major product. So this is the second equivalent. So one equivalent here, first equivalent here, and second equivalent here. So that is the product form. Okay. So I guess this part is clear, beta. Any doubt here?
No, sir.
Right. Last thing you need to understand is about how to make a 1,4 addition in these alkenes and alkynes. 1,4 addition. Okay. So 1,4 addition is usually observed when you have a conjugated dienes. And in case of conjugated diene, if you react with nickel and H2 and heat here, there are two products you are expecting. One with hydrogen getting added here. The other one is hydrogen getting added on these two positions. This is termed as 1,2 addition. The second one is termed as 1,4 addition. This is 1,2 addition and this is 1,4 addition. And the major product is 1,4 addition in this case. Got it? Now, how does it work? See, whenever we have a double bond here and then a metal surface is present here like this, on which there are two hydrogens present here like this. Okay, they have a bond. Now, as they come close to each other, then you will notice that there is a hydrogen at this point, there is a hydrogen at this point, then it is connected to a metal surface here, this way, and there is a bond breaking here, there is a bond making here, there is a double bond movement here, like this, and then there is a bond making here. So instead of six membered ring, a four membered ring, now you have six membered cyclic transition state. So six membered cyclic transition state is always more stable compared to four membered transition state. That's why it will adapt to go for this one. And eventually hydrogen and hydrogen will come here and double bond will form. And this is a cis product form. See, if the molecule is aligned, the double bond is aligned, both the double bonds are aligned towards a metal, then this is called cissoid form. This is called cissoid form. A cissoid form is able to generate a cis product in this case. Clear, beta? So, see this example. So, if you have a double bond and a double bond here, and then I have H2 nickel and heat here, then definitely you will notice that double bond will be formed here, correct? So this is the major product you will get. If you have a double bond here and double bond here with H2 and nickel form and heat, then you will see double bond here, H here and H here. Here also we had H here and H here. So both of them are 1,4 additions. Okay. Now suppose if you have something of this sort, I have one double bond here, but double bond here like this. And then I'm treating with H2 and nickel and heat of one equivalent. Usually 1,4 addition is always first preferred because that will have more reactivity. So this will be the product form. Okay, major product form. Yeah. Any doubt on this, beta? 1,4 addition?
No, sir.
Right. But like I said, this is highly conditional where you have to have a cystoid form. What if there is transoid form? See, transoid form is the case where your double bond is restricted. So I can make a molecule restricted this way because now I cannot make a six-member transition state. So in that case, if you add H2 and nickel and heat here, so now any one double bond you have to add with. So maybe this hydrogen and hydrogen got added. Double bond is here. So what is this addition now? 1,2 addition. So it is only 1,2 addition. So 1,2 addition is only possible in this case. Okay. This is a similar logic you will observe when you have it in anthracene. This is anthracene. So we have a double bond, and double bond like this. And when you treat with H2 and nickel and heat, you can see these two double bonds here. These are in conjugation. So that will make an 1,4 addition in this case. So one hydrogen here and one hydrogen will get added. Double bond will shift here. Rest of the double bonds will remain intact. So this is when you have one equivalent. Okay. Now this one is a more stable compound because you can see left side and right side, both of them are two complete benzene rings. Isolated benzene rings are more stable than fused benzene rings. Remember, I'll put it as a note here. Okay. Isolated benzene rings, isolated benzene rings are more stable than fused benzene rings. Yeah. So I exhausted everything that is to be learned from hydrogenation. So I hope you got an idea about what type of questions that can be asked, what is the stereochemistry behind it. Okay. Now let's go to the next reaction, which is called Wood's reaction. Correct. So we can prepare alkanes using something called Wood's reaction here. Correct. How does this work? How does this Wood's reaction work? Let's see. Suppose if I take 2 moles of alkanes, alkyl halides, react with sodium, then these will get coupled. Alkyl groups will get coupled and NaX will form. It should be done in the presence of ether. Okay. And overall reaction short way is the shortcut to check out is that you can see removal of this NaX and joining these two. Okay. That's how it works. Now let's see the mechanism. The mechanism is of two parts, beta. One is polar mechanism. Polar mechanism. Polar mechanism as in you're expecting the reaction to happen with some ions in nature. So how does that work? Imagine I have 2 moles of sodium added in ether, and sodium is an excellent source for releasing electrons. So it will release electrons into the solution. Now I have Rx here and two electrons are approaching. This is step 1, this is step 2. So these two electrons will approach on R, try to remove this X, and you'll get R minus and X minus. So because they have same charge, they'll repel. And now the third step will be about this R minus, again attacking on Rx as a nucleophile, and this will process via SN2 mechanism, and where you will get R and R plus X minus has been formed. Correct? Now, what are these side products here? Side products you can see whenever you have R minus, see side products are here. Okay. Whenever you have R minus, one important note here is R minus is good, very good nucleophile and extremely strong base. Extremely strong base. And you need to understand one thing. Strong nucleophile will tend always towards SN2, and strong base will always tend towards E2 mechanism. SN2 is a substitution where simultaneous attack and simultaneous removal is happening. Now, what is E2? Now, suppose I'll show you with an example. I have, imagine CH3, CH2 minus attacking on CH3 and CH2X. In this case, any X alkyl halide. Then chances are this minus will take away this H plus, push this sigma bond to make a double bond, remove this chlorine, and thereby I would get this as CH3, CH3 plus CH2 double bond CH2. So what we are doing is an anion converting into an alkane as well as an alkene. Okay, just a second. Sorry, check. So we have CH3 and C2H2. This reaction where elimination is happening, getting a new product, this is called disproportionation reaction. Disproportionation reaction. So in Wood's reaction, you would notice that the side products are disproportionated ones and the main products are substitution kinds. And this is via polar mechanism. The other form of mechanism which is accepted is non-polar or radical mechanism. Non-polar or radical mechanism. Okay. Now, check out first case here. We could imagine like this. Sodium in the presence of ether will become Na plus, releasing one single electron. Second step is about if you take Rx, these one electron can go hit onto the alkyl halide to remove this as R plus and X minus. And third step is about if I take these 2 moles of R dot, they can terminate with each other to convert into this. So this is another way of explaining. Here also the side product could be same side product. Side product can also be explained as the disproportionated form with an example here. CH3 CH2 dot plus CH2H and CH2 X dot here. So here this will undergo homolytic fission, correct? Generating, this will undergo homolytic fission by making a double bond here like this. As it prepares here, so this will become CH3 CH3 plus CH2 double bond CH2. Okay, so we will write this as similar to E2. E2 is specifically done for bases, but this is for radicals. So it is very similar to E2 mechanism. Correct? What has been noticed is that whether you take a polar mechanism or a non-polar mechanism, everything looks exactly same. That's why both reactions are equally accepted. Sorry, both mechanisms are equally accepted when it comes to Woods reaction. All right. So you can take any reaction this way and you can find out whatever products you will get. Now notice this example. Suppose if I take this example where I have to figure out a mixed amount of products. So I have been given CH3, CH2Cl reacting with CH3, CH2, CH3Cl, and then sodium and ether is been given to. What can I write, beta? I can make sure that this can undergo coupling of its own. That's how I can get butane. This can undergo coupling on its own, and that's how I can get hexane. 1, 2, 3, 4, 5, 6. And these two can also undergo coupling with each other, making it as pentane. So 1, 2, 3, 4, 5. These three are mandatory. Then we can see the side reactions also. This can become an alkene here. trying to extract a proton. So we found two products here, CH3 and CH3, and this could also become CH2 double bond CH2. In the same logic, can we apply the other way around also? That is CH3, CH double bond CH2, and CH3, CH2, CH3. Okay, it's a very standard JE question. JE question is that find number of find number of possible products in cross Woods reaction. Sorry, yeah, cross Woods reaction. So how many we'll get? Answer is 7 in the case. So you can see how many? 1, 2, 3, 4, 5, 6, 7. Got it? The similar reactions of Woods is one is fatigue reaction, where you have this aryl benzene reacting with an aryl benzene in the presence of sodium converts into biphenyl. So you can imagine like a dot here and terminate those two. Got it? Woods fatigue means one part is alkyl, the other part is aryl. Okay. So remember this is aryl. It is called aryl halide, and the other part is called alkyl halide. If one is aryl, one is alkyl, then the product will be equal to this kind, alkyl benzene. And if both of them are aryl, but only for iodides if you are doing, only for iodides if you are doing by heating it, then you will get Cu2I2, you'll get Cu2I2 and this compound, biphenyl. You'll get Cu2I2 and biphenyl. Franklin reaction, if you are using zinc and anhydrous, zinc and anhydrous HCl or something, in that case, zinc will try to give out ZnCl2 and all, and couple these two reactions, and you'll get this as R and R. Got it? This is called Franklin's reaction. So you could notice that we can get alkanes similar to that of Woods reaction using Franklin also. And this reaction is valid for both alkyl and aryl. Valid for both alkyl and aryl halides. Next one is Core-Howe synthesis. Core-Howe synthesis was developed. Core-Howe synthesis was developed because of the problems which we were seeing with the Woods reaction. See, the problems with the Woods reaction were these, that we are not able to get one product as a major product. We always get, you will get side products which are of disproportionated. So again, separation is an big headache, as well as the amount of product that you want to get will not be able to achieve. To further, Core-Howe synthesis was designed where you take an alkyl halide, react that with lithium in the presence of ether. Lithium also gives electrons, but very slowly. So imagine like this: if lithium will give electrons to it, it will become Lix, and also becomes R minus Li plus. And this R minus, 2 moles of this R minus, if you react with the cupric salt, cupric chloride, cupric bromide, anything, then you will get R2CuLi is a complex. Complex, how does it look like? It is like this. I have a copper which is coordinated with this R group here on both sides, like this. And it has a minus charge on outside and lithium plus. This is the complex which you will get. Okay. So you will notice that the copper is forming a complex here, right? And LX is formed. This complex name is called as Gilman's reagent. And you can preserve this Gilman's reagent and store it. Now, depending upon what you require, suppose I require some alkyl halide that is of a different kind. All you need to use the Gilman's reagent, and this Gilman's reagent will go immediately attack. This R minus will go and attack here and remove out that X minus. So that's how we'll get R and R dash, RCuLix. Okay. This is with one mole. If I take 2 moles here, 2 moles as in, if at all I take R2 CuLi with 2 moles of R dash X, then we'll get 2 moles of R and R dash plus this Cu will become Cu2, sorry, Cux here, and lithium will become Lix here. So that's how you get the product. Got it? Now, the only demand of synthesis is that it has to go through SN2. Now remember, rate of SN2, rate of SN2 is most feasible when you have the least substituted groups here. That means it has to be methyl halogen or 1 degree alkyl halide or 2 degree alkyl halide. 3 degree alkyl halides is very difficult to make. 3 degree alkyl halide, okay, no reaction here. That is the rate of reaction. So you can see, if I take CH3Li, you'll get this form. You react with this copper, you'll get this form. This is a Gilman's reagent. This is a 1 degree alkyl halide. On 1 degree alkyl halide, easy reaction will happen. Propane will come. Okay. This is major product. Major product. So with Wood's reaction, we were not able to get this propane as the major product. But with Corey synthesis, we were able to generate this major product. And that's the big difference here. Got it? In this case, we are able to generate major product. So I hope you understood this Corey synthesis case. Okay. Now notice few examples in this case, how to work out on Corey synthesis. Suppose if I give you, okay, already made Gilman's reagent. So that is something like CH3 twice CuLi. This is a Gilman's reagent already. And then you are reacting that with aryl chloride here. Then I would say no reaction, because on aryl positions, SN2 will not happen because bond breaking is very difficult. There is a partial double bond character due to resonance. So therefore, no reaction. Similarly, instead, even if you take CH2 double bond CH2Cl, here also I will see no reaction happening. Or if chlorine is a part of a bridge here, like this, let's say chlorine is a part of a bridge position, then also it will have no reaction. And if it is a part of a 3 degree carbon, then also you will see no reaction. Actually, reaction would happen, but the products are different. Okay. So here the products will be different. What will be the products? When you have this substituted alkyl, then E2 mechanism is more favorable, which means you will get CH4 plus this will become an alkene. These are the major products. So substitution is not favorable, elimination is favorable. But suppose if you have another case, another example where I have CH3, CH2 twice, CuLi, and then I'm treating that with alkyl chloride like this, 2 degree. Then chances are I will get CH3, CH2, and this coupled product plus elimination products also can be formed. So CH3, CH2, CH3 can form as a side product, and these two. So these two are major products. These two, okay, both will form. Sorry, this is, let me write down. This is via SN2 mechanism. This is via E2 mechanism. Okay, both would form. Both forms in good amount. If it is 3 degree, only E2. If it is 1 degree, majorly SN2. This is the Korehouse synthesis, how it is to be understood, in what cases, what product you need. Okay. I guess this part is clear enough.
Yes, sir.
Now,
Sir, you
suppose
said in Wood's reaction you can't get major product as propane. Why is that?
right, see, in Wood's reaction, suppose if I take CH3, CH2, Cl, and I have CH3, Cl, and then I use sodium and ether, correct? Now, tell me what are the products I'll get? I'll get the product as CH3, CH2, CH2, CH3. This is one product. I'll get CH3, CH3. This is the self coupling. Then we have cross coupling, CH3, CH2, CH3. Now, tell me, is this coming as major? No, right? The contribution is this one, and this one are equal probables to occur. So the
Hmm.
composition of these three would be almost be the same. You know? So there is no chance we can get only this as a major product. You will get all three.
Okay.
Got it?
Yes, sir.
So therefore, no odd alkanes, no odd main chain alkanes, main chain alkanes can be, sorry, can be achieved as major product, achieved as major products with Wood's reaction. Clear beta? That is the biggest issue here. Arush, I hope you understood. Yeah. Now, next, check out coal-based electrolysis. Fourth important process about coal-based electrolysis. Coal-based electrolysis is about making an acidic salt, right, into alkanes by coupling. So imagine I make an acid and base reaction to make a salt here, sodium salt or potassium salt or anything. Then this salt, when you hydrolyze it, you will get alkane and Na2CO3. See the reaction. At anode, oxidation always happens at anode. So this is an oxidation reaction. Right? Oxidation usually happens at anode. So in oxidation, what is happening? RCO minus is becoming RCO dot plus one electron. So if at all I multiply that with 2, I can also write it as 2 moles of this is giving 2 electrons and converting into 2 moles of RCO dot. Now notice RCO dot on slightly heating or in that presence of electricity, slowly it will decompose into carbon dioxide and R dot. Okay, this is the mechanism. You can see RCO dot. This will turn here, make dot and dot to make a double bond, and this will become R dot. So that's how you will get this as R dot. So 2 moles of this R dot will terminate. And remember, this is always the rate determining step. This is always the rate determining step. And on the other hand, when it comes to cathode, this is all about anode reaction, what is happening at cathode. Let's see. On the cathode, because it is an aqueous solution, you would notice that H2O will be accepting the electrons which have been lost by the acetate group or the carboxylate group to convert into an H2 gas and then become 2OH minus. Okay. So at cathode, H2 gas is released always. At cathode, H2 gas is released. Now again, see the JE question how it is being asked. Okay. How many different types of gases? How many different types of gases are evolved during electrolysis of clear CH3, CH2, CO minus Na plus. Now you know that at anode that will convert into CH3 and CH3 gas as well as some amount of carbon dioxide gas as well as H2 gas which is coming at anode. These two comes at anode and H2 comes at cathode. So how many types? Three types of gases are formed. Yes, some part of CO2 will react with the base and convert into carbonate. Okay, but if the question is asked types of gases, you should report these three because ethane is also a gas. You will get that. Got it? Now notice how the examples work here. See, if you have this propane, like I said, this one, Na2CO3, and what is the other gas we have? H2 gas. This is the gas which you will have. Okay. See, what will happen to the pH of the solution overall? So pH of the solution overall will increase. pH of solution increases over time. Increases over time. Okay. Because as the reaction proceeds, more and more OH minus is being produced, which means more pH has been increased. Notice here CO minus CO minus. So you will remove this carbon dioxide, remove this carbon, dot and dot. Dot and dot will terminate internally and convert into an ethene. When dot and form within the molecule, then intercoupling will not happen, intracoupling will only happen. That means you'll only get alkenes and alkynes in that case. Same way here, if you have 1, 2, 3, 4, and I remove this CO2, dot will come here and dot will come here. These two will terminate. So what do I get? Right? So this will go away. So I'll get 1, 2, 3, 4. So dot and dot are present here. Those two will terminate. You'll get this as cyclobutane. Same way if I remove here and here, I'll get dot and dot here. So you will get this as two dots here and two dots here. That will convert into an conjugated diene. So conjugated diene will be more stable form. If you already have a double bond, dot and dot will be here. So that will convert into a triple bond. If you get dot and dot here, you'll get a double bond and this is the product. If you already have a double bond, you'll get a triple bond. But this triple bonded group on cyclic structure is unstable. So it will undergo dimerization. If it is 3 moles, it will convert into this. If it is 2 moles, suppose only 2 moles are given in this case. Same question is given as 2 moles like this. COK and COK and KES, always electrolysis synthesis. So in that case, I will get this one of 2 moles. 2 moles will immediately terminate into the form of this one. Sorry, like this. This is the form we have. Okay. So by chance, if it was benzene, imagine this is benzene here like this, correct? Then this is called biphenylene. Biphenylene. So this is how the biphenylene is being formed. Okay. So I guess the coal-based electrolysis clear it up how to view, right?
Yes, sir.
Next. Check out what is soda lime decarboxylation, also known as Oakwood reaction, SLDC reaction or Oakwood reaction. To take the same carboxylic salt, react that with NaOH and calcium oxide of 3:1 mole ratio. Then I'll get alkane and Na2CO3. Here also, you would notice RCO minus which is there. You have to heat them strongly so that it will convert as carb anion. Carbon dioxide will be released, carb anion is formed. That is the rate determining step. And R minus, when you treat with H2O, because in solution in water, if you recall here, so when this salt has been forming, that is coming from an acid, so it is slightly hydrated. Calcium oxide is slightly hydrated. So it will take away this H plus, you will get an RH. And OH minus is increased, again the pH of the solution increases. Okay? pH of solution increases over time. Increases over time. Now compare the rate. The rate is compared based on stability of carb anion. So you can notice if you remove this carbon dioxide and make negative charge here, carbon dioxide and negative charge here, carbon dioxide and negative charge. You can see this is a triple bonded carbon, double bonded carbon, and a single bonded carbon. So obviously this triple bonded carbon is more than double bonded than single bonded. So CBA, that should be the rate. Same way, if you have any G is OH, NH2, NO2, chlorine, and hydrogen. And then I have CONA, correct? Remove this carbon dioxide, you'll get minus charge here. Which will stabilize minus charge, which here is withdrawing. NO2 is strongly withdrawing, it has minus I also and minus R also. Chlorine has plus M and minus R, but overall it is electron withdrawing. NH2 is strongly donating, OH is strongly donating. Hydrogen has nothing. So therefore C will be the best, then D, then E, then afterwards between OH and NH2, OH is less donating and NH2 is highly donating in this case. Okay. So that's how you'll be able to figure out what is the rate of SLDC. Right. See, the rate of decarboxylation depends on stability of carb anion. So you can see this reaction also. In this case, getting a negative charge here is anti-aromatic. while getting a negative charge here will be aromatic. So if you notice the rate here, B has to have more rate than A. Next here, getting negative charge on benzene here, getting negative charge here, and getting negative charge here. If you compare, right, then B is more stable because of resonance. A is on benzene with a negative charge, which is sp2 hybridization. And then comes C, which is on sp3 hybridization. So B is greater than A is greater than C. That will be the rate of decarboxylation. Okay, next. So you can see what are the products given here. Benzoic acid can form benzene. Sulfonic acid will form alkane here. So here you will get this as Na2SO4 instead. Okay. So next, just like carbon dioxide here, sulfur trioxide will be released. SO3 gas will be released. So you will get CO2 out, negative charge will come here. Negative charge can make resonance. So that's why you will get 50% of hydrogen with isotopic carbon and 50% of this hydrogen attached on non-isotopic. If chlorine is present at alpha position, at beta position, this is alpha and this is beta position, then first carb anion will come that will push here, remove chlorine. Instead of alkane, now you will get alkene. Same way, even if the OH minus is present, this negative charge will be here, push here, OH minus will be released, and you'll get an alkene. And if you have a bromine at gamma position, that is alpha, beta, and gamma position, then minus charge can attack internally and remove that bromine, thereby giving it as uh, cyclopropane. So instead of getting alkane, these would always convert into this cycloalkanes or alkenes. Got it? Next one, check out reactions of alkanes from Grignard's reagent. Grignard's reagent is making of RMGX. How do we prepare that? You take alkyl halide, react with magnesium in the presence of ether. So you'll get this as RMGX. In RMGX, you notice that R has negative and MGX has positive charge. And this one will have highly negative charge and highly negative density charge here. So that's why it behaves as a strong base. So strong that it can extract proton from any polarized hydrogen. So it can extract hydrogen from water, alcohol, ammonia, acids, and it can become alkanes. Okay. Apart of that, where else you can see here, if you have this group, correct, removing this H plus, you will get a negative charge that will become aromatic ring. This is the ring, aromatic ring you will get. So I'll put H here. Okay. So that will make it, acidic as well. Sufficiently, this hydrogen will become sufficiently acidic. And if it is at this, active methylene position, this is an active methylene position, remove this hydrogen, that is also going to give you alkane. Similarly, if you have an alkyne here, remove this H plus, it's easy to make alkane. Alkenes you can't make it. Phenols you can make. From benzene you cannot make it. I'll write down benzene also. From benzene you cannot extract this hydrogen. Okay, that is not sufficiently acidic here. So this will not be the case either. Along with that, toluene is also not the case. That is CH3. You cannot extract this hydrogen here. This is not sufficiently acidic here. So therefore, these cases you have to avoid. Rest all these cases, water, alcohol, NH2, and all of these, you will get alkanes. Okay. Next, red phosphorus and HI. Red phosphorus HI is the main component of all the reducing agents. It is a powerful reducing agent. Clear? How does the reaction work here? See, red HI, as you heat, it will be a maintaining an equilibrium of H2 and I2. Correct? Here H2, if you are not heating it, you can think in terms of nascent hydrogens in solution. So iodine plus red phosphorus will give you Pi3. Pi3 in H2O will give you H3PO3 and HI is regenerated. So therefore you can increase the source of HI when you take red phosphorus and HI. So small amount of red phosphorus is used so that we keep on generating HI again and again. Okay. So how does the reaction work? If you take an alcohol with red phosphorus and HI, It is about replacing one oxygen with two hydrogens. So that makes it alkane here, correct? So every time we have an oxygen here, if you want to replace it, I require two hydrogens to convert into water. So therefore, two hydrogens here. Next, you to replace this oxygen, I require, two hydrogens here. So to make this as H2. But at the same time, after removal of oxygen, I require to put another two hydrogens here to convert into alkane. So therefore, total how many nascent hydrogens required here? Four. So I would require four nascent hydrogens here, correct, to convert into an alkane. Nitriles. Nitriles, directly you can add uh, two hydrogens here and two hydrogens here. That makes it again 4 moles. So 4 moles of nascent hydrogens, correct? Acid, if you notice the acid, to convert this into RCH3, I have to get 2 moles of H2O out because there are two acids. So you can see there are 4 nascent hydrogens here and there are 2 more nascent hydrogens added here, correct? So total how many? 6. So 6 nascent hydrogens are totally added in this case for acids, correct? And sorry, this is about acids. Now check out if you have an aldehyde or ketone, it is the same thing. You will require 4 hydrogens here plus H2O. So any of the groups, acids and acid chlorides and esters, everything can be converted into alkanes. Suppose if you notice glucose here. So glucose, you can see glucose has a structure as aldehyde with 1, 2, 3, 4, 5. 5 pentahydroxy aldehyde. So if you take glucose and react with red phosphorus and HI, this has to get reduced. So 4 nascent hydrogens are required there. Plus here we require 2, 2, 2, 2 and 2. So 5 2s are 10. So 10 nascent hydrogens are required. Total how many? 14 moles of HI is required. 14 moles of HI is required to convert glucose into N-hexane. Got it? Next, Clemenson's reduction. Clemenson's reduction is when you take zinc mercury amalgam and add with concentrated HCl. Okay. So what happens wherever there is an aldehyde or a keto form, that will convert into an alkane. That will convert into an alkane form. Again, this mechanism is not very, appropriate to discuss now because this has a lot of applications in the aldehydes and ketones topic. As of now, we just need to remember it that this reagent will be able to convert any aldehydes and ketones into alkenes. Now, if you already have a chlorine present here, right, and a double bond O here, so this will get reduced. Chances are this chlorine will also get reduced because zinc and mercury, if you give it in excess in the presence of HCl, this will create nascent hydrogens. And that nascent hydrogen can also give you alkene. So it depends upon whether you're giving excess or not. If excess is not given, you'll stop it here only. If excess is given, you'll go up to alkanes. Same way, aldehyde is there, you convert into alkanes. Ketone is there, you convert into alkanes. Here also double bond is there, you convert into alkanes. Again, if it is excess, Cr is in excess, then I can convert that into alkane as well, like this. This is the final product. Okay. Next one, if you notice, Wolff-Kishner reduction. Wolff-Kishner reduction is also converting aldehydes, ketones into alkanes, but by using hydrazine in the presence of base or alcoholic KOH or RO minus. You can use glycol also instead of alcohol. See here, Wolff-Kishner, this will get reduced. If there is any chlorine here, this chlorine can be used as an elimination reaction. That means in the presence of alcoholic KOH is present here or glycol is present, it will convert into an alkene. So this will be the major product in case if there is chlorine present. Okay. If no chlorine, nothing will happen here. This is alkane, and here again, same logic. First reduction will happen. After that, chlorine will be removed out, making this as a double bond and double bond. This is the major product you will get. Got it? So this is about Wolff-Kishner reduction. Next one is about reduction using lithium aluminum hydride and NaBH4. These two are very powerful reducing agents by providing H minus. Okay, provides hydride ions, H minus ions. Correct. So you can see if you have RCl react with LAH and make an SN2 mechanism, you'll get this as alkane RH. Reactivity is methyl greater than 1 degree, 2 degree, and 3 degree. That will be the reactivity in this case. Similarly, SBH, that is sodium boron hydride, if you react, it will go via SN1 mechanism. First, carbocation will form, then H minus will come and attach. Reactivity is 3 degree and 2 degree. 1 degree, no reaction here. Here, 3 degree also no reaction. So basically, no alkane will form here. So in fact, if you have a 3 degree group here like this, I'll write it as an example. If you have a 3 degree alkyl halide and if you use lithium aluminum hydride, you will get an alkene instead. This will be the major product and not an alkane. Similarly, if you have a 1 degree alkyl halide with sodium boron hydride, then there is no reaction because 1 degree hardly reacts, 2 degree and 3 degree carbocations can form. Next, we have specific reaction which can give for all 1 degree, 2 degree and 3 degree. See, 1 degree, 2 degree or 3 degree, any alkyl halide, if you treat that with triphenyl tin hydride, TPH, it will always convert into an alkane. Okay. This is industrially very strongly used for making alkanes. So if you have 1 degree, 2 degree or 3 degree, in all the cases you will happen. Just the rate of reaction will be better for 3 degree because it will go via hydrate formation also, then 2 degree, then 1 degree, and then methyl also. All these will can react. All right. Next one, if you have sodium and ethanol with alkyl halide, again the reactivity here is SN1, so CH3 greater than 1 degree, then greater than 2 degree, no 3 degree will happen. Yes, this is similar to that of lithium aluminum hydride. Zinc in acid, base, or ethanol. Acid, base, or ethanol. In all the cases, zinc has much easier way to generate nascent hydrogens, and that will convert any alkyl halide into alkanes. Correct? Any alkyl halides into alkanes. Okay. Lastly, if you notice carbides have, suppose if a carbon graphite is being treated with H2 in electrical spark, you will get this is acetylene form. Correct? Same way, if you have calcium carbide reacting with water, you will get this acetylene form. And if you take Al4C3, this will give you 3 moles of methane. So anything which is forming methane, then that particular carbide is called as methanide. If it is forming propine, it is called propanide. If it is forming ethene, it is called ethanide. So CaC2 is ethanide, this is methanide, this is propanide. Got it? Okay. That's all, beta. We'll stop.